The United Nations has released a new update confirming that 3I Atlas has been officially placed under a planetary defense observing exercise, an unexpected move that immediately triggered global attention. The sudden designation by the International Asteroid Warning Network, IAWN, contradicts NASA's calm public stance, which maintains that the interstellar comet shows no signs of danger and behaves exactly as expected. Yet, despite NASA's reassurance, the UN has activated a full-scale coordination effort involving international observatories, space agencies, and even spacecraft near Mars, creating a wave of questions the public can't ignore. If the situation is truly routine, why initiate a level of monitoring normally reserved for high-complexity objects? Why is the world's planetary defense infrastructure mobilizing at this scale while officials insist everything is normal? The timing, the intensity, and the secrecy behind the exercise have fueled speculation that authorities may be preparing for something they are not ready to reveal, leaving 3I Atlas as the most closely watched and most mysterious interstellar visitor humanity has ever encountered. As the exercise was announced, the scientific world immediately shifted its focus toward the comet itself. 3I Atlas, formerly designated C2025-1, had already been recognized as only the third confirmed interstellar object ever detected. The first two, Oumuamua in 2017 and 2I Borisov in 2019, were rare enough, but 3I Atlas arrived with an even more unusual combination of factors: an active coma, volatile outgassing, and a long observational window that made it uniquely accessible to telescopes across the globe. On paper, these traits made it an excellent candidate for an observing campaign. Yet the timing of the UN's move suggested that the decision was being driven by more than just convenience. Inside observatories and planetary defense offices, teams began reorienting nightly schedules to track the comet's subtle motion against star fields. Astrometry, the precise measurement of its position, became a central task. Unlike asteroids, which appear as point-like sources of light, comets have sprawling, diffuse coma that make pinpointing their centers notoriously challenging. This complexity is part of why IAWN selected 3I Atlas for the exercise. It forces the global network to push its tracking capabilities to the edge, as would be necessary in the event that a dangerous comet with a poorly constrained trajectory were ever discovered. Officially, the exercise's purpose was to refine those skills. Unofficially, observers couldn't help but wonder whether 3I Atlas had exhibited behavior that warranted closer attention. Astronomers familiar with IAWN procedures were quick to point out that these exercises occur roughly once a year, each using different objects, asteroids, near-Earth objects, or comets, to test the readiness of the global network. Yet 3I Atlas stood apart. It wasn't just any comet, it was interstellar, unpredictable, and full of unknowns. Observers noted that its outgassing patterns fluctuated more sharply than expected, creating brief periods of increased brightness that complicated the long-term modeling of its behavior. These variations weren't alarming on their own. Many comets act similarly, but in combination with the UN exercise, they fueled public curiosity. What exactly did scientists see in the data? What justified an international drill of this intensity? The answers may lie in a growing list of anomalies that continue to surface as more researchers and independent observers examine the comet. With every new image, measurement, and frame posted online, 3I Atlas reveals yet another characteristic that doesn't quite fit the familiar template astronomers use to describe comets. This does not mean the object is artificial or exotic, but it does mean that its behavior is unusual enough to attract global scrutiny. The more the data accumulate, the more the comet stands apart from what scientists expect an interstellar visitor to look like. The first anomaly emerged at the moment of discovery, when 3I Atlas was first detected in July 2025 at roughly 4.5 astronomical units from the Sun. Its brightness was surprisingly high for an object still deep in the outer solar system. Most interstellar bodies discovered at that distance appear faint, sometimes barely above the background noise of the star field. Yet 3I Atlas stood out with a luminosity that suggested either a larger nucleus or unusually vigorous activity well before typical sublimation thresholds. That detail alone did not imply anything extraordinary, but it became the earliest sign that the comet might not conform to the standard behavior astronomers observe in slow-warming long-period comets. As orbital measurements were refined, another irregularity came into focus. The comet's path was clearly hyperbolic, confirming it originated outside the solar system, but its inbound trajectory aligned unusually well with the plane of the planets. Interstellar objects typically enter from random angles, reflecting the chaotic distribution distribution of matter scattered throughout the galaxy. A near-ecliptic approach is not impossible, but it is statistically uncommon. Combined with the brightness anomaly, this alignment contributed to the growing suspicion that 3I Atlas occupies a narrow space between what is expected and what appears to be unfolding.
More details surfaced when higher-resolution imaging began flowing in from observatories worldwide. Long-exposure frames revealed subtle jet-like outflows extending from the coma. In most comets, these jets move as the nucleus rotates, creating smeared or curved features over long exposures. But certain jets in images of 3I Atlas appeared unusually stable. They held nearly identical positions across sequences taken hours, and in some cases days, apart. This stability suggested either a very slow rotation period or an outgassing pattern that did not rotate with the nucleus. Even after image stacking and calibration, the directionality remained coherent. That consistency, alongside the early brightness anomaly, helped solidify the first cluster of irregularities that researchers could no longer dismiss as minor quirks. Infrared spectroscopic data added a new dimension to the puzzle. Measurements indicated that the coma was dominated by carbon dioxide, with an unusually high CO2 to H2O ratio compared to typical long-period comets originating in the outer solar system. While CO2-rich comets are not unheard of, the proportion observed in 3I Atlas suggested a formative environment where thermal history starkly different from what scientists see in solar system-borne objects. Perhaps it formed in a CO2-dense region of another star's protoplanetary disk, or perhaps it experienced chemical changes during an extended journey through interstellar space. Neither explanation is confirmed, but both reflect the strangeness of its composition and the limited parallels available for comparison. As perihelion approached, image sequences revealed that several jets retained fixed orientations, even as solar heating increased and the coma expanded. Under normal conditions, the peak of activity introduces greater variability, causing jets to rotate, fan out, or scatter unpredictably. This time, the features held steady. The persistence of these structures elevated them to one of the most puzzling characteristics observed so far. Across different observatories, different instruments, and different nights, the pattern repeated. The consistency ruled out instrument error and processing artifacts, pointing instead to a real physical phenomenon taking place within the comet. While these scientific anomalies were building a compelling pace for deeper investigation, an entirely different shift was happening in the source of information reaching the public. NASA continued releasing cautious updates, framing the comet's behavior as broadly consistent with normal cometary activity. But the most detailed, frequent, and revealing observations were not coming from official sources. They were coming from amateur astronomers.
This spontaneous, globally distributed group began producing images with a cadence and transparency unmatched by any institutional release schedule. Equipped with telescopes ranging from small backyard reflectors to remote automated systems, amateurs captured a steady stream of long exposure frames revealing the comet's evolving morphology. Many of these images showed the same stable central brightness profile appearing in professional data, but amateurs were posting their images within hours of capture, bypassing the editorial delays of formal reporting pipelines. As more amateurs joined the effort, image quality improved, coverage expanded, and the observational timeline became almost continuous. Some documented faint, sideways-oriented jets that contradicted simple solar-driven outgassing models. Others recorded brightness fluctuations too subtle to appear in composite images. Many stacked exposures across multiple nights to reveal details, such as slight asymmetries in the inner coma that could easily be overlooked in isolated observations. The openness of these contributions transformed the amateur community into a real-time analytical network. Raw frames, calibration files, exposure logs, and processing notes circulated freely. Observers reviewed one another's work, reprocessed shared data, and validated findings across different instruments and atmospheric conditions. This workflow, peer-to-peer, transparent, and immediate, stood in stark contrast to the curated, measured updates released by major institutions. As a result, many anomalies gained traction first through amateur posts before they appeared in professional literature. Persistent side jets, stable orientations, faint vent structures, and brightness oscillations were often identified, shared, and analyzed publicly long before they were acknowledged in formal releases. For researchers following the comet closely, amateur data became a primary reference point. Even professionals monitoring the object began consulting amateur imagery to fill temporal gaps or confirm subtle morphological changes. This inversion of the traditional flow of information where the public now informs itself through its own observations rather than waiting for official summaries has significantly shaped the narrative surrounding 3I Atlas. Instead of a slow trickle of institutional data, the comet's evolution is visible in real time through hundreds of community-generated frames. Information moves horizontally rather than vertically, shared directly between observers and interested onlookers. Taken together, the anomalies of 3I Atlas form a pattern that pushes the object far outside the boundaries of what astronomers consider standard comet behavior. Its anomalous early brightness at discovery, its statistically unlikely inbound alignment with the solar system's plane, its persistent and directionally stable jets, and its unusually CO2-rich composition all contribute to a portrait that resists easy explanation. Subtle, non-gravitational accelerations, measured repeatedly in astrometric data, deepen the mystery. The comet's motion is being influenced by forces that do not match the expected behavior of a rotating, naturally venting nucleus. Post-perihelion imaging only sharpens the puzzle, revealing jet orientations so fixed and coherent that they do not appear to respond to the usual rotational mechanics at all. If 3I Atlas ultimately turns out to be natural, then it represents a type of interstellar comet fundamentally different from those previously documented. In that scenario, the object broadens our understanding of what icy bodies from other planetary systems can be, how they form, how they evolve, and how diverse the galaxy's population of wandering debris truly is. Its journey would prove that interstellar comets can follow rules unfamiliar to us, shaped by conditions alien to our solar system. But if certain anomalies remain stubbornly inconsistent with natural models, then 3I Atlas may be signaling phenomena not yet recognized by comet science. That does not confirm anything artificial, but it does suggest that this object might be governed by rare or unknown physical processes, unusual internal structures, exotic chemical layering, or thermal histories that defy current understanding. Such ambiguity is precisely why the United Nations has taken an unprecedented step, elevating a comet to a planetary defense priority and activating coordinated global monitoring usually reserved for potential impactors. Regardless of how the data ultimately settle, 3I Atlas is altering the landscape of both scientific inquiry and planetary defense policy. It has become the first interstellar visitor to trigger a unified, planet-wide response. Agencies are cautious in their wording, emphasizing routine observations, but the scale of the coordination, the international alerts, the IWAN mobilization, the Mars-based tracking assets is unmatched. It reflects an unspoken acknowledgement this object is unusual enough to demand vigilance.